This device is called a double suspension pendulum. If the pendulum's weight is displaced in the longitudinal direction, only the lower part of the structure will oscillate. But if the weight is displaced in the transverse direction, the entire structure will oscillate. In the second case, the effective length of the pendulum becomes greater, which means the oscillation frequency decreases. Now, let's displace the weight diagonally. And it traces out a complex shape trajectory, which results from the combination of longitudinal and transverse oscillations. Let's fix the camera to the upper crossbar, record this motion, and trace the trajectory. We see that the pendulum's weight describes a repeating pattern which is called the Lissajous figure, named after its discoverer. Let's figure out how such figures are formed. Here, the red circle is attached to the blue rectangle, and the blue rectangle performs horizontal harmonic oscillations. Therefore, the center of the red circle traces a horizontal straight line. Now, let the red circle oscillate along the blue rectangle at the same frequency. Its center again traces a straight line, but now it is tilted relative to the coordinate axis. If the horizontal oscillations follow a sine function and the vertical ones follow a cosine, the red circle will move not along a straight line, but along an ellipse. And if the frequencies of the horizontal and vertical oscillations do not match, the trajectory of the red circle becomes more intricate. After all, now one cycle along the horizontal no longer corresponds to one cycle along the vertical. In this upcoming experiment, we will be dealing with two separate pendulums. An additional weight is carefully attached to the first pendulum, so its oscillation frequency will actually be higher than that of the second one. The signals from the two rotation sensors are fed into two inputs of the workstation. As the pendulums swing, the displacement of the first pendulum will be displayed horizontally on the screen, and the second one vertically. Let's set both pendulums in motion, and a characteristic line appears on the screen. If there were no damping, this line would fill in a rectangle whose dimensions would correspond to the amplitudes of both pendulums. But here, due to damping, both amplitudes gradually decrease. Lissajous himself obtained these figures in an experiment with a beam of light, reflected from two mirrors attached to two tuning forks. In this setup, one mirror oscillated horizontally and the other vertically. As a result, the beam in the optical tube moved independently in both directions at once. If the tuning forks are tuned to an octave, their frequencies are in a ratio of 2:1, so for every two oscillations in one direction, there is one oscillation in the other direction. If the tuning forks are tuned to a perfect fifth, their frequencies are in a ratio of 3:2, so for every two oscillations in one direction, there are three oscillations in the other direction. If the tuning forks are tuned to a perfect fourth, their frequencies are in a ratio of 4:3, and the image on the screen takes on this appearance, just like in our very first experiment.